Welcome back. In this section, we're going to talk about the generalized ARCH model, or simply the GARCH model. To explore it thoroughly, we're going to discuss the intuition behind it, introduce the mathematical notation, and then try fitting it to the data. Let's begin. I already gave you a teaser of what this GARCH model represents. It's an extension of the ARCH, where we add past conditional variances to the variance equation. The intuition behind this comes from observations of volatility clustering, where you can notice patterns of consecutive periods of low and high volatility in the returns plot. Therefore, if we include the conditional variance from last period, we'll have a sort of benchmark on what to expect. Of course, this wasn't always true for returns, since they could jump and drop from one period to the next, while volatility is continuous and doesn't behave like that. Now that we've grasped the intuition behind the model, let's continue with the equation for the volatility model. Notice that we use volatility model and variance model interchangeably. This is due to the fact that variance is our measure of volatility, so the two are equivalent in this context. Suppose we have a variable y, and we want to apply the simple GARCH model on. Then the equation will read as follows. The variance of y in period t dependent on y in period t minus 1 is equal to omega plus alpha 1 times epsilon in period t minus 1 squared plus beta 1 times sigma squared in period t minus 1. So let's go over all the components of this model, just as we did with the simple ARCH. The left side of the equation states that the variance today is conditional on the values of the variable yesterday. Next in line, we have omega, which is the constant term for the model. In ARCH, we had a single series of independent variables, so we call this constant alpha null. Here, however, we could potentially have two, the squared residuals and the conditional variance. Thus, to avoid confusion, we use an unambiguous coefficient name, omega. We continue with alpha 1 and epsilon t minus 1 squared. These represent the squared residual for the past period, as well as its coefficient, alpha. I believe you're familiar with this from the last section. In the end, we have beta 1 and sigma squared, t minus 1. The latter represents the conditional variance from last period, while the former is the numeric coefficient we're trying to estimate. Of course, since these models are time-dependent, this past conditional variance can also be expressed as a sum of former squared residuals and another variance. We'll discuss this in detail in less than 20 minutes from now. When we first mentioned the concept of the GARCH model, we compared it to a parallel of the ARMA model. So next time, we're going to explain some further similarities between the two. Thanks for watching. Hello again. Last time we said our goodbyes after mentioning the similarities between this new GARCH model and our familiar ARMA. In this lecture, we're going to talk a bit more about this and draw several parallels to help you comprehend the idea behind the GARCH better. Let's start with number of orders. The simple GARCH model has two orders, an ARCH order and a GARCH order. The former represents the number of past squared residuals, while the latter, the number of past conditional variances. Therefore, the equation we witnessed is the volatility equation for the simple GARCH 1-1. Of course, the ARMA model also contains two orders, one for the past values and one for past residuals. Since we're measuring conditional variance with the GARCH components is essentially an AR component. Moreover, the ARCH component takes square residuals, while the MA expressed past errors. The former is just a squared version of the latter, and since variance is squared measurement, the two are essentially equivalent. Next up, let's look at the order of notation. We have the ARMA PQ and the GARCH PQ. In both, the P expresses some form of past values, while Q expresses some form of error terms. In a way, the GARCH is a sort of squared ARMA model for the error terms of the mean equation. However, there are also complex ARMA-GARCH models which combine the two. When it comes to such models, we use an ARMA PQ for the mean equation and a GARCH PQ for the volatility equation. It's important to note that the P and Q orders of the two don't necessarily have to match. For instance, we can have a single GARCH component in the variance equation while using 3 AR aspects in the mean expression. This distinction is important because it gives us great flexibility when choosing the best model to describe our dataset. Now that these parallels are clear, we're ready to fit a GARCH 1-1 with serially unrelocated mean. Thanks for watching. Hello again. In this lecture, we're going to fit a GARCH 1-1 model with serially uncorrelated data. In case you're wondering what that is, it's just the formal way of stating that the mean model doesn't rely on past values or errors. Essentially, this is just a constant mean model. Now that this is clear, let's get coding. We don't need to import any new packages here. The same method we used for the ARCH will suffice in fitting a GARCH model, so there's no need for a new library. In case any of you need a refresher, the library was called ARCH, and the method ARCH_model. So, if we want to fit a GARCH 1-1 with serially uncorrelated mean, we simply need to call the above-mentioned method and use the appropriate time series as an argument. That's because the default values for most of the arguments are exactly what we want them to be. The mean model is set to be constant, the volatility model is set at GARCH, and the orders P and Q are set to 1. Even though this is incredibly convenient, good practice dictates we specifically set the values for these arguments, as it would make trying out other GARCH models much easier. So, we should set the model GARCH1 variable equal to ARCH model, parenthesis, DF returns, from 1 onwards, comma, mean equals constant, comma, vol equals GARCH, in quotation marks, comma, P equals 1, Q equals 1. Once we specify the model, we fit it and store its results in a new variable, which we will call results GARCH 1-1. Remember to set the frequency for the iteration updates to some higher value, like 5 or 10, to avoid displaying unnecessary values on the screen. And in case you need a hint, we do so by giving a value to the updateFreq argument. Next on our list, we simply need to check the summarized statistics of the model, and we're ready to comment on the coefficients. For starters, we see that this model took 13 iterations to converge. This is more than twice the number of computations it took for the simple ARCH to do the same, which was 6. However, if we check out the log likelihood value, we see that it is even greater than the one we reached for the ARCH 12. This suggests that adding a single past variance gives more predictive power than 11 squared residuals. I know such a comparison sounds like an advertisement for some dishwashing liquid or laundry detergent, but we noticed a similar pattern when going from the MA to the ARMA. That said, including past values as a form of baseline provides much greater accuracy, which also explains the higher likelihood of our predictions. Now, since all the coefficients are significant and we get a higher log likelihood, this model instantly becomes our frontrunner for measuring volatility for the time being. We say for the time being because we're yet to see how higher order GARCH models perform. Stay tuned, because we will do that in the next section. Thanks for watching. Hello there. Last time we examined how the GARCH 1-1 performs in measuring the volatility among price returns. In this lecture, we're going to focus on higher-level GARCH PQ models. Okay, before we begin, we want you to know it's been mathematically proven that no higher-order GARCH models outperform the GARCH 1-1 when it comes to variance of market returns. This is due to the recursive nature in which the past conditional variances are computed. Including 1 not only makes it redundant to include past squared residuals, since it already captures the effect, but also makes other conditional variances obsolete. From a mathematical point of view, all the effects of the conditional variance 2 days ago would be contained in the conditional variance yesterday. So there would be no need to include more than one GARCH component. The precise algebra behind this proof falls outside of the scope of this course. However, keep in mind that all you need to know is that including all higher order GARCH models is not necessary. Anyway, it's always best to question what you are told, so let's quickly test a few of these models empirically. Before we begin, we need to draw your attention to a potential pitfall of the ARCH model method. In it, the P and Q notation for the order arguments is flipped. In other words, P represents the ARCH order and Q the GARCH order. One explanation for this is because when we write out the GARCH equation, the ARCH components usually come before the GARCH ones. In short, if we want to fit a GARCH PQ model, we set the P argument equal to Q, and vice versa. Of course, it doesn't really make a difference when it comes to analyzing returns, since the GARCH 1-1 is the optimal choice. However, if you're examining other types of time series, remember to take this predicament into account when you use the ARCH model method. We've learned what we needed to know, so let's fit the GARCH 1-2. The only adjustment we should make is to set the Q argument to 2. Then we can jump directly to the volatility model of the summarized table to see something extremely interesting. We observe a p-value of 1 for the beta 2 coefficient. This means we have a case of full multicollinearity due to the relationship between conditional variances, which we explained earlier. We can try the GARCH 1-3, but we are bound to get the exact same p-value for both beta 2 and now beta 3 as well. This is all truly fascinating, but let's see how the GARCH 2-1 performs. Even though we don't get a p-value of 1, we can still see the additional coefficient is not significantly different from 0 at the 5% significance level. Therefore, we should avoid using this method. Regardless of that, we can decide to be brave and even go a step further by trying the GARCH 3-1. If we do so, we get a p-value of 1 for alpha 3 and a p-value greater than 0.05 for alpha 2. This means both are not significant, so we know this model fails as well. This hands-on experience gave us further proof that the GARCH 1-1 is the best model for measuring volatility of returns, and there's no need to rely on overly complicated models. Thanks for watching. Hello again. Up until now, we've seen how to conduct time series analysis manually, because this is how much of the empirical analysis in the field is conducted. But what if we could skip all of that? What if we could run some code and get the best model instantly without having to compare AICs and log likelihoods? That would save us a huge amount of time and allow us to be more precise in our analysis. On the one hand, having such a tool at our disposal would eliminate a big chunk of the time needed to go through different models one by one. On the other, we won't be able to peek behind the curtains and understand our data really well. Finally, it should be noted that borderline cases would be treated in a standardization fashion, essentially neglecting our domain expertise. In the next section, we'll see how to automate the model selection process, and we'll discuss the pros and cons that go along with such approaches. See you all there, and thanks for watching.